So before going into the in-depth discussion of this topic, let me give you the introduction regarding similarity of two matrices. A matrix A is said to be similar to another matrix B. A is said to be similar to the matrix B if there exists a non-singular matrix. If there exists a non-singular matrix P such that A can be written as P B P inverse. Okay, then A is said to be similar with the matrix P. Now when A and B are similar, then they share many properties. For example, eigenvalues of A will be same as eigenvalue of B. Okay, if eigenvalues are same, immediately what you can claim, that means trace of A will be same as trace of B. Determinant of A will be same as determinant of B. Okay, likewise there are few properties which will be shared if two matrices are similar. Okay, and the notation is this: A similar to B. Now see, in the discussion of diagonalizability, this concept of similar matrix, it is required. A matrix is said to be here you can consider this one as an important result. A matrix is said to be diagonalizable. That means A is diagonalizable if A is similar to some diagonal matrix. If A is similar to some diagonal matrix, that is, in some other words, A can be expressed as P D P inverse for some non-singular matrix P. So what is this P? We'll see. And this D matrix, D is a diagonal matrix. That means D will have some component like this. That means diagonal entries will be present here. Rest of the entries are 0. Okay, so this is the idea of diagonalizability. That means A is diagonalizable if A is similar to some diagonal matrix. Now what is the mechanism and what is the process to find or to check whether A is diagonalizable or not? That we'll discuss in the subsequent part. Now, what is the biggest advantage of having this relation, that is A is equals to PD P inverse? What is the advantage? So for example, suppose find A power K. Okay, find A power K. If we have this question, that means K, you can consider this one as a large number. Okay, so in that case, see, just if A is diagonal, if A is diagonalizable, that means if A is similar to D, then immediately what you can write as per this discussion, A is equals to P D P inverse. This thing you can write. Okay, now just see here, A square. If you want to find A square, that means P D P inverse multiplied with again P D P inverse. So if you do this, what you have, see, P D P inverse into P. Here you have D P inverse, and we know that P D, here P inverse into P means identity into D P inverse. So from here what we have, P D square P inverse. Just see what you are getting. A square is equals to, A square is equal with P D square P inverse. Likewise, if you proceed, what you will be getting, see, A power K is same as P D power K P inverse. Now see, the calculation, it is a very simple calculation here, because D power K, it is nothing special. See, D, if you have suppose A B C and here all the entries are 0, suppose. Okay, so D power K means here A power K, B power K and C power K. Quite easy. Okay, so likewise we can easily find A power K from this relation. That is one of the biggest advantage of having A as a diagonalizable matrix. Now see how to find or how to check whether A is diagonalizable or not. So for that, this result you should know that if A is diagonalizable, then it satisfies this condition. Okay, that means from here what you can write, see, if you just do the post multiplication, that means AP is equal with PD. You should check this one whether it is satisfying or not. Now what is P and what is D, that we'll discuss. Now see here, first thing, A is a n cross n matrix. Okay, A is a n cross n matrix, that means it is a square matrix. So first work, that means step 1, find eigenvalues. Let A is 2 cross 2 matrix. Okay, for the time being we are considering A as 2 cross 2 matrix. Find the eigenvalues, that is for 2 cross 2, suppose lambda 1 and lambda 2, these are the eigenvalues. Okay, step 2, find the respective eigenvectors. Okay, eigenvectors, that is suppose corresponding to lambda 1 v1, corresponding to lambda 2 v2. Okay, so here eigenvalue and eigenvector, these are the initial two steps. Now step 3, here this matrix P, it is v1 v2, just write them in column wise, that is P. And D is what? D is that lambda 1, here lambda 2, 0 0. Okay, this is D and this is P. Okay, once we have this P and D, then step 4, you just check whether AP is equals to PD, this is holding or not. If AP is equals to PD, then immediately what we will claim that A is equals to PD P inverse. Okay, PD P inverse. So from here you can say A is diagonalizable matrix, that means A is similar to some diagonal matrix. Okay, and D is that diagonal matrix. Fine. So this is the mechanism to check whether A is diagonalizable or not. Okay, here I have taken n as 2 just for the simplification purpose, nothing else. So now we can take question and check whether the given matrix it is diagonalizable or not. So first question you can write here. Check the matrix given by 106 minus 1 is diagonalizable or not. Okay, this is the question. So solution, here A is this matrix 1 0 0 minus 1. Okay, so here A is what? A is a lower, here 6 you have, so this is a lower triangular matrix, lower triangular or upper triangular matrix or diagonal matrix. For them the principal diagonal entries will be the eigenvalues. So lambda 1 equals to 1 and lambda 2 is equals to minus 1. These are the eigenvalues we are having. Okay, this is lower triangular matrix, so directly we can write it. Okay, so here corresponding to lambda 1 is equals to 1, let us find the eigenvector. So A minus 1 into I multiplied with x is equals to null vector. So here what we have, 1 minus 1 0, 6 minus 1 minus 1. here x was x1 x2, here what we have 0 0. So from here what you can write 0 0 6 minus 2 x1 x2, here we have 0 0. So from this if you do the calculation, what you will get 6x1 minus 2x2 0. So from here x2 is equals to 3x1. So let x1 is equals to suppose t, so x2 will be 3t. Alright, so from here what you can write that t 3t, and equivalent to that you can write 1 3. So here it is clearly visible that 1 3 is one eigen vector corresponding to lambda equals to 1. This is one eigen vector. Say this is v1. Say this is v1. Okay, as per our notation. Now similarly we try to find for lambda 2 is equals to minus 1. Let's find it. So a minus of minus 1, that means a plus I x equals to null. So from here what is that matrix? 1 plus 1 0 6 minus 1 plus 1. Here we have x1 x2, here 0 0. So from here what we are getting 2 0 6 0 x1 x2. So here 0 0. So now if you solve this one, you will be getting x1 equals to 0, that's for sure. So x2 we can take, suppose this is s, so here let, okay, so immediately you have the vector as 0s. So equivalently you can write s 0 1. That means it is clearly visible that 0 1, if you put s equals to 1, this is one eigen vector corresponding to lambda equals to minus 1. So as per our notation we can write this one as v2. Okay, so far what we did, we have the eigen values and corresponding eigenvectors just got. Okay, so now next we need to set p and d. Okay, so p, it is v1 and v2, just write them like this. So v1, what is that v1? See 1 3 1 3, and here you have 0 1 v2, and d is what? D is lambda 1. Lambda 1 is what? Lambda 1 is 1 and lambda 2 is minus 1. Just see the order. Okay, so here v1 v2, here lambda 1 lambda 2. This is p and this is d. Now we need to check ap, whether ap is equals to pd or not. Okay, a is that matrix given as 1 0 6 minus 1, and p is 1 0 3 1. So you just do the calculation, matrix multiplication. So here you have 1, here you have 0 0, here 6, and here you have 3, here 0 minus 1. Okay, and similarly pd, just calculate that pd part. So p is 1 0 3 3 1, and d is what? 1 0 0 minus 1. Do the calculation. So here you have 1, here you have 0, here 3, here you are getting 0 minus 1. Just see, this is ap, this is pd. So from here you can draw the conclusion that ap is equals to pd. So from here a is equal with p d p inverse, post multiplication with p inverse. So you can say that a equivalent or a is similar to d. That means that is A is diagonalizable. Okay, this is how we check whether the given matrix it is diagonalizable or not. Okay. Similarly, another question I am giving, you can try this question. Try for, let me give you a simpler example. Okay. So this is again a upper triangular matrix, so eigenvalues are immediate. Okay, that means 1, 3 and 2. Find out eigenvector, check whether AP equals to PD holding or not. Okay, so this question you can try. Okay, so now we'll be solving a question from 3 cos 3. So check the diagonalizability for A is equal with 1, 3, 3, minus 3, minus 5, minus 3, 3, 3, 1. Okay, so we'll try to find the eigenvectors first. Okay, so eigenvector, if you try to find eigenvalues, so eigenvalues are given by A minus lambda I is equal with 0 determinant. So here 1 minus lambda 3, 3, minus 3, minus 5 minus lambda minus 3, 3, 3, 1 minus lambda is equal with 0. So here minus lambda cube minus 3 lambda square plus 4 is equal with 0. That means this is after simplification I got this one. You can verify this. So here lambda cube plus 3 lambda square minus 4 is equals to 0. So from here, if you do the calculation, you will be getting lambda equals to 1, minus 2 and minus 2, like this. You will be getting this one. Okay. This one. So here lambda 1, 1, lambda 2, minus 2, lambda 3, minus 2. These are the values we have. These are the eigenvalues. So corresponding to lambda 1 equals to 1, let us find A minus 1 into I, x equals to null. So corresponding to this, if you want to find the eigenvectors, so what will be that? So 1 minus 1, 3, 3, minus 3, minus 5, minus 1, minus 3, 3, 3, 1, minus 1. Here you have x1, x2, x3, 0, 0, 0. So here 0, 3, 3, minus 3, minus 6, minus 3, 3, 3, 0, x1, x2, x3. This one. So from here, what you are getting, see, from the first part, 3x2 plus 3x3, here minus 3 x1 minus 6x2 minus 3x3, 3x1 plus 3x2, here 0, 0, 0. Okay. I think this one you are getting. Yes. So from here x2 plus x3 0, x1 plus x2 plus x3 0, x1 plus x2 is equals to 0. Okay. So from here what you can have, see, x3 is equal with minus x2. Here if you are taking this, so x2 or x1 is equals to minus x2. Okay. So from here we are getting this relation, and if you just consider this one, x3 is equals to minus x2 and x1 equals to minus x2, here in this equation, so this equation will give you x1 minus x2, here plus 2x2, here again minus x2 is equals to 0, that means 0 equals to 0, that is fine. So we can have, see, x1 is equals to minus x2, x3 equals to minus x2, and x2 we don't know. Okay, so basically from this relation what you can write, see, from this relation, say let x2 is equals to s, so x1 will be minus s and x3 will be minus s as well. So from this setup what you can write, that x1 minus s, x2 s and minus s. So this is equivalent of writing, if you are taking suppose minus s common, so 1 minus 1 and 1, this you are going to get. Or if you are taking suppose s common, so minus 1 1 and 1, minus 1. So for the time being we can take, that is 1 minus 1 1 is 1 eigenvector corresponding to lambda equals to 1. There is nothing special. See, you can take s common, and in that case minus 1 1 and minus 1 would be one eigenvector. Okay, so that we can take, not a big deal. Now this is one eigenvector, and similarly for lambda equals to what, lambda equals to minus 2, for lambda equals to minus 2, if we want this a 2I x equals to null, so now this is 1 plus 2 3 3 minus 3 minus 5 plus 2, here minus 3 3 3 1 plus 2, so x1 x2 x3 we have, so here 0 0 0. So here what we have, see, the next step 3 3 3, here minus 3 minus 3 minus 3 3 3 3, here we have x1 x2 x3, that is 0 0 0. Now from here if you do the calculation, basically you are going to get x2 plus x3 equals to 0, this one. So from here what you can write, see, x3 is equals to minus x1 minus x2. Now see here what you have, one equation, one independent equation and 3 variable, so 3 minus 1, that is 2 variable you have to assign. This is the case. See, if number of variable it is suppose n and number of independent equation it is m, which is less than n, so n minus m, this number of variable you have to assign. Okay, this is one important note, you should make a note about it, that n is number of, suppose number of variable, and m is number of equations. So n minus m number of variable you have to assign. So here suppose let x1 equals to t and x2 is equals to suppose s. Okay, so x3 what we are getting, minus t minus s. Okay, now let's write this one in formal way, that is here what we are getting, that x1, what is that x1 expression, x1 is t s minus t minus s. So this can be written as t times 1 0 minus 1 plus s times 0 1 minus 1. Just see, you can do this calculation from the right hand part and you will get back this one. Okay, so basically this is one eigenvector and this is another eigenvector corresponding to lambda equals to I guess minus 2, corresponding to lambda equals to minus 2. So we can take, suppose for the time being, we can take here this one as v2, this one as v3. Okay, so that is 1 0 and minus 1, 1 0 and minus 1. Here just let me check it once. So x1 t, x2 my s, and x3 minus t minus s. So this is, and this one 0 1 and minus 1 are two linearly independent eigenvectors corresponding to lambda equals to minus 2. So now that is p is going to be, what is that p? P is v1 v2 v3. Just write down those two. v1, what is v1? v1 is 1 minus 1 and 1, 1 minus 1 1. Here what you have, 1 0 minus 1 and 0 1 and minus 1. This is p. And d is what? D is corresponding to, see, first we got the eigenvalues as lambda equals to 1 and then minus 2 and minus 2. So 1 minus 2 and minus 2. So we have this one, this. Okay, this is p and d. Now we need to find ap. We'll check this one, ap. So what is our A matrix? 1 3 3 minus 3 minus 5 minus 3 3 3 1 A into P. So 1 1 0 minus 1 0 1 1 minus 1 minus 1. So you find this here. So 1, here you have minus 3 plus 3, so 1. Here 1 0 minus 3, so minus 2. Here 0 3 minus 3, so 0. Here 3 plus 5, here minus 3 plus 5 minus 3, so you are going to get minus 1. So here minus 3 0 plus 3 0, so here 0 minus 5 plus 3 minus 2. All of you do the calculation by yourself. 3 minus 3 1, 3 0 minus 1, so 2. Here 3 0 3 minus 1 2. So let's check whether P is equals to PD, it is there or not. So P is 1 1 0 minus 1 0 1 1 minus 1 minus 1. D is that matrix 1 0 0 0 minus 2 0 0 0 minus 2. So if you do the calculation here, 1, here minus 2, here it is 0. So here we have minus 1, here 0 0 0. So here 0 0 minus 2, here we have 1, here we have 2, and here 2. So both are same. So AP is same as PD. So AP is equal with PD, that is A is equals to PD P inverse, that is A is a diagonalizable matrix, A similar to D. Okay, so thus we can easily solve this type of question, either second order or third order as per the given problem. We can easily find the eigenvalue, eigenvector, construct P and D matrix. After that, just check this property and you are done with the solution. Okay, so that's it from this basic understanding of diagonalizability. If you have any doubt or question, and you can drop your question.